before past midnight. Okay, so that's all I care about is this. I don't care about anything else. No other calculations matter right now. That's all I need. All my information is summarized here. So first, I have to graph the asymptotes. If we graph a function, did I start? Yes, I did. So if we graph a function with asymptotes, we have to graph the asymptotes first. So there are two asymptotes, a horizontal one at -1 and a vertical one at 2. Then I have 2 points, basically. I have 0, 0, and I have 1, 1. But 1, 1 is a whole. So the function is coming from approaching the horizontal asymptote. It's increasing all the time, increasing to 0, 0, going through the hole, and approaching positive infinity. So from -1, crossing at the origin, going through the hole, sort of, you know what I mean. And that's on the left-hand side of the vertical asymptote. On the right-hand side of the vertical asymptote, the function is coming from -infinity, increasing to -1. From -infinity, increasing to -1. So therefore, the function is, what was it, x minus x squared, 2, I think, plus 3x minus x squared. I put it back as they gave it to us, which I don't have to, but. Any questions on this? Once you practice this, and we practice more problems, and we look at more problems, it really isn't a big deal at all. So the key is to factor everything, present everything in descending order, simplify not before you state the domain. State the domain, get the table going, talk about the function first, everything you can find about the function, move on to the first derivative, study the sign, find critical numbers, if any, and then move on to the second derivative. And once you put all these together in a table, then you will have no difficulties in graphing it. Any questions? Any questions? Questions for me?
So I know the chapter is called Application, but
yes.
Where would something like this, where could it be applied in like a real life?
Oh, very good. I'm logged out from the other computer also. I mean, always, as you know, my school computer. Okay, and I can't see whether I'm uploading here or not. Okay, it is uploading. Okay, so where will this particular application be important? That was the question, correct?
Yeah, correct.
Number one, this first application is super important for understanding the in detail of a function, because you can say, well, I can graph it with a graphing calculator and I punch it in and I get the graph and I'm done. True, but you understand the concepts here are coming together. The concept of the first derivative, what does that say about the function? The concept of the second derivative, what does that say about the function? So this gives you a perfect, let me switch to the other camera. That gives you a perfect understanding of how we are able to, a perfect understanding of the function, number one. Number two, you may be interested in working in data analysis in studies like rational functions. It's a very good question. Rational functions have a lot of applications. So I just did the rational functions with my college algebra, and I just want to show you, since you're asking about rational functions, and I'm going to switch the camera to show you applications. If we don't understand these functions, we're not going to be able to, in case you're interested in working in data collection and analysis of functions, right? Function analysis. So for example, this is a rational function. So horizontal asymptotes, vertical asymptotes, if any. This is another. This is a when a patient is injected with a concentration, with a particular drug, and the concentration of the medication in the bloodstream. So understanding all this function, limits, horizontal asymptote, and etc., they're all coming from this. Here's another example. This is an example of the pH level. So in this class, I'm doing with them a lot of applications, and these are all rational functions. So this is a rational function. It models the pH level of the human mouth X minutes after a person eats food containing sugar. And this is again a rational function. How would you find this minimum? If you don't know how to find the first derivative and find critical numbers, you're not going to be able to find this minimum unless you say, oh, but I have a calculator. Right, but what happens here is that this is a minimum because the first derivative changes sign, and this is a critical number, from negative to positive. And this is typical for the first derivative. So understanding real-life situations and models, this is a very, very important step in applications, if you want, or applications of differentiation. Extremely important. Without having a strong understanding here, you're going to get this graph with a graphing calculator, but the understanding will not be solid. I have a lot of students who say that they're using this in a lot of applications. One student said that he's doing something like this, but way more sophisticated at NSA. So there are a lot of applications, especially these functions, rational functions. Does that satisfy you somewhat?
Yeah, absolutely. That, I think, just hearing you say that, like the example about the pH,
right,
seeing it and then you explaining it kind of made it,
yeah,
like, a little bit,
and you know exactly what happens there. And you know why. See, in this class, it's college algebra. In this class, I cannot talk about inflection points.
Right. Yeah. Yeah.
But
I mean, like I can look at the graph and like see those things.
Right.
I guess understand them. So.
Yes. Yes. So that was 3.5. So with them, I cannot talk about an inflection point, but we know that there must be an inflection point somewhere here, because the function opens up and it has to open down in order to approach the horizontal asymptote. There is no function that approaches the horizontal asymptote like this. It has to approach asymptotically, getting closer and closer to it. But I can't explain to them an inflection point because this is not a calculus class. So they understand this minimum, but from this point on, they don't know that the function opens up and at some point it has an inflection point and all of a sudden it changes concavity. They don't understand that. The same thing here. I mean, I guess I can mention that, but they will not understand why there is an inflection point. The same thing here. The function opens down, but then all of a sudden it has to open up because it has to approach asymptotically y equals 0. But you understand that when you look at the function now, you know what's happening there. And you know how to find the point where it changes concavity, but they don't. And the calculator will not give you. No calculator that I know of, maybe the ones that are not allowed to use in calculus classes, maybe those can determine the inflection point and can solve the equation the f second derivative equals 0. But this one does not, as far as I know. So, so when it comes to inflection points, maybe you can determine, right? We know we can determine max min with this. But inflection points, no way, when it changes concavity. And today, actually, let me see if I have this, yeah, close by. Today I talked to them about the exponential function. So again, this is college algebra. So I talked to them about the exponential function. So this was what we compared with base greater than 1, with base less than 1, the two possibilities and the two shapes. And I was telling them, which is such a sad story, that we wish the virus would follow this exponential function. But actually the virus follows this exponential function. And one day there are 10 people, and the next day there are 1,000, and the next day there are, 50,000. Because this is the fastest increase possible. Exponential function. Depending on the base, of course, but this is the fastest increase. So the virus follows an exponential function with a base greater than 1. And that's what we saw. It really broke my heart when I saw those mass graves on Saturday. But I shouldn't mention that. Sorry about that. Okay, moving on then. Our next step, and as I mentioned to several of my students, you are my therapy. Not that I need therapy, but with you, I forget about other things. Okay, so we looked at the rational function. We're back. So the summary, which is section 4.5, is exactly what we just did. I pay attention to that because they don't present any summary. So when you read this, you should summarize all the information in a table because they don't present that. But we are going through each and every step here. We're going through domain, of course, x and y intercepts. Symmetry, yes, we just talked about that. Asymptotes, yes, we have to. Then intervals of increase or decrease, local max min, concavity, and points of inflection, and sketch the graph. So these are all the steps that we followed just a few minutes ago. Okay, just gave me a warning on the side. I wish I could show you what I'm doing. I'm uploading the last video for the last class so I can delete everything else. Okay, so this was literally everything in section 4.5. Is it enough? No. We are going to go back to it when we get there for more examples. Now, I would like to continue with 4.4. 4.4 goes back to L'Hopital's rule. And you can say again, yes, only because there are other indeterminate cases that we can work with L'Hopital's rule that we have not seen before. Okay? So, 4.4. Indeterminate cases. Indeterminate cases. And of course, again, indeterminate cases and L'Hopital's rule. We know what L'Hopital's rule means. Let me just start with that, just refresh your memory. Only in the situation of 0 over 0 or infinity over infinity, and only in a limit when x approaches a from, let's say, a polynomial at the top and a polynomial or a function in the denominator. It doesn't have to be just polynomial. It can be a trig function or anything. Only in these two situations, then we can write this. This is never the case. That we never differentiate a ratio like that, ever. But inside the limit, applying L'Hopital's rule, only if we have 0 over 0 or infinity over infinity, we are allowed to do that. So now let's go back to the indeterminate cases. There are 7. So we looked at 0 divided by 0, we looked at infinity over infinity, we looked at infinity minus infinity. I don't think we had anything else so far. Have we seen anything else? I'm looking, I don't think so, right? I don't think we did anything else. So these are the ratios, this is the difference. Here are the powers, 1 to infinity, 0 raised to 0, infinity raised to 0. So 2 ratios, 1 difference, 3 powers, and 1 product. Yes, that's what it was. We did look at the product, I think. These are all 7 indeterminate cases. This one is a problem with L'Hopital's rule. These two, first of all, I'm saying that this one most probably cannot be changed into these two. So L'Hopital's rule for the difference will not work. I don't want to say in all cases. Maybe there is a case in that which I can change this into a ratio. I don't know. But careful with this. All the other ones, whenever I can change them into these two, I can apply L'Hopital's rule. So 3 powers, 1 product, 1 difference, and 2 ratios. So a total of 7. So now all we want to do in this section is just simply practice L'Hopital's rule with the other, which are more sophisticated. So these are the most difficult ones. This one is easier. These are the nicest. And this one may never work with L'Hopital's rule. So I may not be able to apply L'Hopital's rule here. These are the most difficult ones to change into that. We are still sticking to the rule. Only when I can change these into these two, I'm allowed to use L'Hopital's rule. When I can change this into one or the other, I can use L'Hopital's rule. As they are, only in these 2 cases. So that's all we need to do in this section. Just choose, look at how many different problems, 66 different problems they came up with for L'Hopital's rule. So let me choose the first one, and then we'll practice with whatever you would like to choose. So I'm going to choose what caught my eye, this 26. Well, let's see, 26. And then please choose the next one. We are on page 308. We are working with L'Hopital's rule and the indeterminate cases in the entire section. That's all we care about. And this is page 6. So 26, again page 308, and we're looking at limit as x approaches 0 from hyperbolic sine x minus x divided by x cubed. It's a ratio. I'm really hoping for one or the other so I can immediately find the answer with L'Hopital's rule. If that's not the case, maybe I can make some adjustments, maybe algebraically, who knows? I don't know. So for now, let's just plug it in. Hyperbolic sine 0, we know the graph, but let me just refresh your memory. This is a combination of exponential functions, e to negative x minus e to x divided by 2. So when I plug 0 in here, this is 1 minus 1, over 2. So that would be 0. So this approaches 0, this approaches 0, this approaches 0. Not bad. So we are looking at 0 over 0. Okay, so then I can apply L'Hopital's rule directly. So this is limit Sx approaches 0. We remember that hyperbolic sine prime is hyperbolic cosine. I differentiate x and I get minus 1. I differentiate the denominator and I get 3x squared. Now, hyperbolic cosine is a different story, right? So it has plus. So hyperbolic cosine is e to negative x plus e to the x divided by 2. So when I plug in 0, then I have 1 plus 1, 2 over 2. So this is 1. So this approaches 1. 1 minus 1, the numerator is 0, the denominator is still 0. I'm in business. I can apply L'Hopital's rule again. So this is limit as x approaches 0. When we differentiate cosine, remember there's no change in sign there. Hyperbolic sine. 1 differentiated is 0. 3x squared prime is 6x. Okay, I'm back in business. It's still 0 because I had the same thing. It's 0, still 0 over 0. And I differentiate again. Limit as x approaches 0. Hyperbolic cosine, sine is hyperbolic cosine. I differentiate the denominator and I get 6. I am finished with this because the numerator approaches 1 and the denominator is 6. So the answer is 1/6. So I chose, I'm getting a sip of water. I chose a simple example in which we had a ratio. L'Hopital's rule was right there. We didn't have to do anything. We did apply it, however, 3 times in a row. But the answer was 1/6. So now we're ready to continue with